Good afternoon. Happy Wednesday. Hope everybody had a rejuvenating day yesterday. I did. It was nice not to come in. Got some grading done, got some other things done. But back at it now. One more stretch till Thanksgiving, and then we'll go online. I still owe you some sort of survey asking your opinions about what we should do for the last couple weeks. Look for that in the next few days. Other than that, Kappa Thursday, Kappa tomorrow as usual. Just plug along. Here we are. So we were doing on Monday examples of how adding energy to a system can not only change its temperature, but also change its phase. And we were doing some examples where we have to think about both of those things, changing a sample's temperature and changing its phase, and then sometimes changing its temperature again, and how the energy it takes to do change in temperature cannot be used to change the phase and vice versa. It takes energy to change the temperature without even changing the phase. There's some true or false questions on this week's homework assignment, and I haven't gone over all of them. And in fact, there's one particular one that might be kind of confusing, and that is there's a true false, which is something like there are 0 materials for which it has been found that, or every single material that's ever been discovered expands when you heat it up. It turns out that's false. 99.9% of materials expand when you heat them, but there's a very prominent one that has a very narrow temperature regime, at least, where that is not the case. You may know what that substance is? It's water. Think about this. Why do ice cubes float? I didn't hear what you said. Because they're less dense with water. What does that imply? That they have gotten bigger instead of smaller as you cool them off. It turns out that water is fairly normally behaved. It gets denser and denser, meaning it shrinks when you cool it down further and further and further until you get to about 4 Celsius. And then the turb actually turns over and it starts expanding again as you cool it below 4 Celsius, which is really important. One, it's why your ice cubes float in your soft drink and in your water, but 2, it's why ice on ponds and lakes forms at the top and not at the bottom first. And this turns out it's very important for preserving life in ponds and lakes, because if it formed at the bottom first, it would very quickly form to the top, and all life, all fish, marine life in the lakes and ponds would freeze and die. And so it allows an insulated layer on the top where it can be a little bit warmer and stay above freezing at the bottom and stay a little bit liquid. The pressure change doesn't hurt either. And so allows for fish and things to live even over a frozen pond over the winter. So water, being weird again in its various ways, tends to be beneficial for life in all the ways that it's weird. Anyway, that's a fun counterexample to the normal rule where you heat things up and it gets bigger. Okay, let's do another problem type. By the way, if you haven't done the attendance today, please do that if you're sitting in the room. It's easy to lose track and not remember to do this, but let's try to keep track and remember to do this. Zoomers, I just got a message that my internet connection is unstable. So somebody, if it goes out, I may not notice. Text somebody in the room and they can let me know, and I'll get it back up and going again. All right, so let's do another problem type. And that is interactions of 2 systems. You're not seeing this, are you? The Zoomers are seeing it. Okay. This should start up in about 10 seconds. Interaction. So I've done problem type : interaction between 2 systems. Interactions of 2 systems. Sorry? Yeah, it's going to come up in a second. It's warming up. There it is. So what do I mean? I mean, let's say, here's an example. Hot water pulled into a cold container. And usually the question will be, what is the equilibrium temperature? So what happens, right? You pour hot water in a cold container, and there is a lack of thermal equilibrium. Energy is transferred from the hot water to the cold container continuously until they reach its thermodynamic equilibrium. What does that mean? It means the temperature is the same everywhere. Assuming usually that this is some insulated thing where there's no net energy in or out, you're just transferring water energy from the water to the container. It will eventually settle down into a constant temperature. Oh, we're back. Sorry, Zoomers. Hopefully you're still there. I'm going to start sharing again. Go ahead, ask your question. Right. So naively, you might think that it's just the average of the two temperatures. But what if you have a tiny amount of hot water in a huge cold container? Or what if you have a gigantic amount of water in a very thin-walled container, right? It's going to depend on how much mass there is in the water and in the container, and it's going to matter what the heat capacity, the specific heat is of the water and of the container. So it won't necessarily be an average unless those two things happen to be exactly the same. But I lost it again. No, I didn't. I'm good. Okay, you're still there. Great. Okay. So this is a fairly simple thing to do, but it's easy to get confused by signs. So whenever you're doing a problem like this, be thinking about the signs. We will be doing some reservoir. So this one is an example of not a reservoir. Right. So what is a reservoir? A reservoir is something that has so much heat capacity, capital C, that anything you attach to it isn't going to change its temperature, right? So that's a simple problem. If you put something in thermal contact with a heat reservoir, its final temperature will be the temperature of the heat reservoir, right? I'm talking about two things that are not reservoirs being in thermal contact with one another. What is the final temperature? We will get to reservoirs later, but that's going to be in the process of energy transfer and heat flow, and not thermal equilibrium, right? Okay. So these are usually isolated systems. What do I mean by isolated systems? Close this. What do I mean by that? I mean that, yes, we poured hot water into a cold container, but we're not allowing any other heat transfer, like from the air. We put the whole thing in a box that is, maybe that would be helpful. Sorry, Zoomers, I keep crashing out. I've just plugged myself into wired Ethernet though, so hopefully that'll help. Okay, hopefully you're back. Okay. So what I was just saying, isolated systems, meaning we're putting the whole thing in an isolated container and we're not allowing any energy in or out. So what does that mean? It means that Q tote equals 0. There is no energy. Whatever energy you brought into this, you stay with it. The energy that you're adding from the external is 0. You're only transferring energy between things in your system, right? So 0 equals Q tote, and this has to be equal to the energy added to the water plus the energy added to the container. So what does that imply? It implies that the energy in the water, the energy change of the water, the net heat that you've added to the water, has to be the negative of the net heat that you've added to the container. This is where the sign can get confusing. You're going to be very tempted when you start these problems to say Q water equals Q container, because whatever energy is lost by the water is added to the container. The negative sign is really important, and it's really easy to miss. We'll see when we do this problem how those negative signs can get really easily messed up. That negative sign is really important, and if you forget it, it won't necessarily be obvious. You'll get an answer. That answer will just be wrong. Okay? So this negative sign is very important. I'm going to do like 6 arrows pointing towards it. Maybe I'll make one of them red. Okay. I'm even going to write, tempting to write QW equals QC. It is not. Make sure, if you're going to write that in your notes, make sure there's a big circle around it with an X over it, because that's not right. Okay, don't do it. The energy that is gained by one of these has to be lost by the other. There has to be a negative sign in there. Okay. So you can write this out. So when you do this, you get QW equals negative QC. You can expand each one of them. You get C, the specific heat of water, times the mass of the water, times delta T, is equal to the negative of the specific heat of the container, times the mass of the container, times delta T. I should put W, because those are different M's. One of those is the mass of the water, one of those is the mass of the container. So delta T, again, you've got delta T's here, so you can do, so delta T is always T final minus T initial. CW, MW, T final minus T initial. And usually, the initial temperatures will be different, right? T initial water will be different than T initial ice. This is negative C container times mass of the container times T final minus T initial of the container. Right? So these two T finals will be the same, this one and this one. Usually you'll be given everything else, you can solve for T final. So let's try one of these examples. It's going to be a little bit different. It's going to be exactly the opposite. I'm going to put a hot object into a cold bath to try to heat it up. So maybe if you don't have a hot water heater in your house and you want to take a warm bath, you could imagine building a fire in your backyard. You could imagine putting rocks in that fire to heat them up to very hot temperatures. You could imagine putting those rocks into your bathtub to heat the water to make for a pleasant bath. So that's the problem we're going to do. We have very hot rocks and we put them into a bathtub of water. What is the final temperature of the water? And is it comfortable for getting into? So, example. Take rock out of fire, put it in bathtub, with room temperature water. So here's some data. The mass of the rock, pretty big rock, we'll call it 5 kilograms. Decent sized rock. Volume of the water. Yeah, how much bath? Well, we wanted to get warm, so let's not make our bathtub too big. This is gonna be one of those giant jacuzzi ones. Let's say it's 0.2 cubic meters. It's gonna be a pretty sparse bath, but you know, we're living in primitive times. So what is the mass? We don't want volume of the water, of course. We want mass of the water. What is the mass of the water going to be? Mass, of course, is just the density of water times the volume. We've got 1,000 kilograms per cubic meter times 0.2 cubic meters. You get 200 kilograms. So already you can see we've got a lot more water here than we have rock. So it's going to be hard to heat this thing up. Some other data that we might need to know: C of the rock, The specific heat of rock is 0.2 kilojoules per kilogram times Kelvin for typical silicate kinds of rocks. We know that C of the water is the heat capacity of water, 4.2 kilojoules per kilogram Kelvin. So this is another point where we're going to have a hard time heating this water up. It takes a lot more energy to heat up a kilogram of water than it does to heat up a kilogram of rock. So what's the temperature of the fire? Let's say it's 500 degrees Celsius. It's a pretty hot fire. Let's say our temperature of the water, these are the initial temperatures, of course, is 20 degrees Celsius. That's pretty close to room temperature. Okay, great. So we can say Q water equals negative Q rock. Don't forget the negative sign. Very important. We can plug these in. We've got C water, M water, T initial water, sorry, T final water, it's just T final. T final minus T initial water is equal to negative CR MR, R standing for rock, TF minus TI rock. Okay, let's solve this thing symbolically first. We can expand these two temperature terms. This is gonna get a little bit messy, CW MW TF minus CW MW TI water is equal to negative CR MR TF plus CR MR TIR. Let's bring all the T final terms over to the left and bring all the other terms over to the right. We've got CW MW TF plus CR MR TF equals CR MR TIR plus CW MW TIW. You can see why, if you had forgotten that negative sign, you wouldn't really have any intuitive sense. You would have a negative sign wrong here, right? There would be a couple of negative signs there where I have positive signs now. It wouldn't be obvious if this were wrong at this stage of the game. You could continue on calculating merrily along, even though it's going to be completely wrong at the end. You're going to get a T final. It's just going to be a nonsensical T final. So again, forgetting that negative sign at the beginning, it isn't going to be obvious until you get to the very end that something has gone wrong. And it might not even be obvious then, although it should be. Okay, so let's combine these two. We're solving this thing for TF. TF times CW MW plus CR MR equals, we got this whole thing going on over here where nothing really is the same. CR MR TIR plus CW MW TIW. And then we can solve for TF, basically divide through CR MR TIF TIW, oh, TIR, dang it, plus CW MW TIW, all divided by CW MW plus CR MR. You can see how we've gotten to a place where you're basically taking a weighted average. It is basically an average. You're taking the average of the temperature of the initial temperature of the water and the initial temperature of the rock and dividing by some combination of the two, but you're weighting it by, of course, how much is there and what the specific heat of that substance actually is. You're weighting it by the heat capacity of those two substances, basically. This is just a weighted average. Okay, that's the final answer in symbolic terms. You could throw in some numbers and see what this gives you. If you do the whole top part out, I'm not going to bother to write the intermediate numbers. You get 17,300 kilojoules degrees Celsius per Kelvin divided by Actually, I think it is instructive. I'm gonna do the intermediate steps so you can see. I'm actually not gonna convert degrees Celsius to Kelvin because I don't have to, because these are gonna be delta T's. So I won't have to actually convert to Kelvin if I don't want to. Let me actually show you how this works. So I got 0.2 kilojoules per kilogram Kelvin, that's CR, times MR is 5 kilograms, mass of the rock, times the initial temperature, 500 degrees C, plus 4.2 kilojoules per kilogram Kelvin, times 200 kilograms, times 20 degrees Celsius. All of that divided by 0.2 kilojoules kilogram Kelvin times 5 kilograms plus 4.2 kilojoules per kilogram Kelvin times 200 kilograms. Okay, now, as I was saying before, you might be tempted to want to convert both of these degrees Celsius into kelvins. You don't have to do that. Why? Because there's a per Kelvin on the top and on the bottom. Those are actually going to go away. You don't have to cancel the degrees Celsius with the Kelvin on top. And because we're always talking about a delta T, we can treat that delta T as if it were a Kelvin anyway, even though we can't hear, and have it come out right. So this becomes 500. What are the units of this? So I'm doing this term here specifically. 0.2 times 5 times 500 is actually 500. What are the units here? Kilograms cancel out. I've got kilojoules degrees Celsius per Kelvin, which is weird, plus 16,800, same unit, kilojoules degrees Celsius per Kelvin. All of that divided by 2.5 kilojoules per Kelvin plus 840 kilojoules per Kelvin. I forgot, 842.5. Got ahead of myself. 842.5. So, no, it's just 840. Dang. I got ahead of myself again. 5 times 4.2 times 200, 840. The whole thing on the top is, so you can see, right? This is showing you, this is the total energy for the rock. This is the total energy for the water. There isn't going to be much difference here. And this is some weighting thing on the bottom. Add those two numbers on the top, you get 17,300, again, kilojoules degrees Celsius per Kelvin divided by 8. This is where I get 842.5 kilojoules per Kelvin. And now my kilojoules in Kelvin just go away and I'm left with degrees Celsius. I didn't ever have to change it out if I didn't want to. And again, this is a delta T, you can use it back and forth. Okay, divide those two numbers and what do you get? 20.5. So your water started out at 20 degrees Celsius, and after adding this rock at 500 Celsius and waiting for things to come to thermal equilibrium, your bath temperature is up to 20.5 degrees Celsius. Not sadly a very, you're gonna have to add a lot of rocks to this thing if you wanna make a comfortable bath for yourself, even at 500 Celsius. Okay, so bottom line of all of this stuff in this part of the is negative sign. Don't forget the negative sign. It doesn't even matter which side you put it on. It'll work out either way. It just has to be a negative sign on one side of the equation when you do these, all of the energy being transferred from one to the other problems. Okay. So, let's move on to another topic, and that is methods of heat transfer. And anytime I say heat, I really mean thermal energy. It turns out there are really only 3 ways to transfer thermal energy from one object to another object. Does anybody know what one of those 3 ways is? Conduction, yes. And how would you define conduction? Only 3. So 1, conduction. That's exactly right. Touching things together. This is energy transfer by contact. What's actually going on? You put a pot on a stove, right? An electric stove. You know how electric stoves work. Current gets passed through a metal plate. That metal plate gets really hot, and you can use it. You can put your pot of water on top of it, and it will heat it up. Right? What's physically happening between the metal in the stove and the metal in your pot to cause that energy to transfer? Yeah, that's exactly right. The atoms in the stove are moving much faster than the atoms in the pot because it's gotten really fast. And specifically, the electrons are moving really fast, and the atoms. And those atoms interact with the first surface layer of atoms on the pot and heat them up, and energy is transferred between them. And then, of course, it's transferred through all the layers of the pot and into the water. And eventually, if you wait long enough, you can get the thing starting to boil. Microscopic interactions between particles at the boundary, basically, is what's going on with conduction. So our EG, I don't know if this is begin A, EG, pot on electric stove. But there are, I could name 100 examples off the top of my head on how conduction works, or examples of conduction. Anytime you have 2 surfaces in contact that are different temperatures, you're going to be conducting energy between them. Okay, there's 2 more. Anybody know another one? Go ahead, Zoe. Convection. Exactly. How would you define convection? Or how would somebody else define convection? Sure, but you could make that same definition for conduction too, probably. Its surroundings. There's something specific that's happening in convection that's different than conduction. So density difference in a fluid will certainly be a cause for convection to occur. You need some sort of density gradient for convection to happen. But okay, so but that's not how I wouldn't describe that as what convection is, though. Can anybody give me an example of convection? Absolutely. Magma heating up in the Earth's core, getting less dense, becoming buoyant in the other stuff that's around it, and physically moving upward. That's a method of transferring energy from the Earth's core outwards. It happens on the sun too. The outer layers of the sun, the exact same thing happen. There are layers below that heat up, become buoyant, get a change in density, rise to the surface, and carry that energy with it. That's what we mean by convection. You've seen this also in perhaps bowls of, if you've been to a Japanese restaurant, miso soup. You can see this pretty well because there's lots of particulate matter in miso soup. Usually the soup will cool off on the top first, and you'll get convective cells happening where hot blobs at the bottom rise and distribute their energy and then sink back down to the bottom. That's a way of transporting energy from the bottom of the soup to the top of the soup. Not really, because conduction, though the atoms themselves don't move. They're just interacting with one another. In convection, the atoms themselves move. This really is energy transport by bulk motion of stuff. Energy, I'll say E, transport, transfer. That's an E. I'm bad at writing today. By bulk motions. Do you have a question, Isaac? Yes, at certain levels. Although so also, if I mail my grandmother a hot bowl of soup, that is technically convection, right? Because that is energy transport. I'm moving my hot energy, my hot soup, moving the entire thing from one location to another location. That's energy transport by bulk motion. That's technically convection by this definition. It's not convection in the way we've just been talking about it in some physical process that would be set up naturally that way, but it would be considered convection anyway. So convection is more broad than what you just defined it to be, but certainly in the ways that we think about it in a natural phenomenon and setting, it's not a bad way to think about it. Did you have your hand up? Exactly right. And then it transferred to conduction as the Brack sat there in the bathtub. There might have been some convective currents that allowed the so get back to your point. You can certainly have two iron bars that are exactly the same in composition and exactly the same in mass and everything, have them at different temperatures, put them in contact with one another, and they will transfer energy to one another by conduction, right? So it isn't just this kind of the material. But anytime you have bulk motions like that, right? Whatever you have, if it, let's say it was a vat of liquid or gas, or it doesn't matter even what the substance is, although you're right, it's hard to do this with solid. Anytime you start mixing it, very, very quickly it's going to become homogenized if you're doing convection on the whole thing. And so, yes, it's hard to imagine a situation where you have vastly different things. You're transferring energy between vastly different things by convection, because it will be homogenized almost instantly. Does that answer the question? Do you have another one? Okay, all right. Yeah, that's right. It would be transfer from one location to another location within a substance or within a distance. That's right. So hot air rising examples, hot air rising, FedEx guy delivering hot soup, etc. I'll say sun, outer part, Earth's interior, etc. There's lots of different ways. Miso soup, you get the idea. Okay, there's one more. Let me know what the last one is. Go ahead. It would be radiation. Exactly right. Certainly, usually EM radiation, although not necessarily EM radiation. Any kind of radiation will work. So what do you mean by that? Energy transport by light. Although in this case, I am saying light, so I am talking about completely EM radiation. You could imagine, maybe you couldn't imagine. Maybe it is just light. I'll stop before I get myself into trouble. It turns out that all objects with temperature greater than 0, and by that I mean all objects, there are no objects whose temperature is equal to 0 or less than 0, emit an electromagnetic emit EM radiation. All of them. And so this table, that desk, me, you, the lights, we're all emitting light as we speak. And therefore we are losing energy as we speak by emitting that light. We are also, as we sit here, absorbing light. And so often if we're in equilibrium, we're emitting as much as we're absorbing and we're not changing in temperature. But if that ever gets out of whack and we're emitting more than we're receiving, or we're receiving more than we're emitting, that can actually be a net temperature or energy change to me or you or the table, which will cause that temperature to change, which can cause that temperature to change. So constantly losing energy, but radiation is being absorbed. Is being absorbed also. Increasing the energy. So it's a balance of how much you're emitting and how much you're absorbing on what your temperature is, what your equilibrium temperature will be. Okay. So we're going to be focusing on 2 of these in this class, specifically conduction and radiation. Convection is interesting. If you want to learn more about convection, you can take my stellar astrophysics course. For you guys, that will be in the fall, except for Bailey, in the spring of 2023, your senior year, second semester. But it's kind of complicated. We still don't fully understand it. It's really difficult to parameterize. And aside from some very important astrophysical and geophysical applications, not that terribly important for most physics applications. So let's focus on the other 2 and going through them as best we can. So let's start with conduction. The bottom line on conduction, how much energy you pass from one to another, the energy transfer rate. The bottom line, if you know one thing about conduction, it's this. Is proportional to the change in temperature between the 2 things that you're putting in contact with one another. So again, remember how this works. You've got 2 objects that are not at the same temperature. You put them together into contact and they will transfer energy between them. How fast that energy transfers between them is proportional to, linearly proportional to the temperature difference between them. The higher the temperature difference, the faster that energy transfer will happen. So heating rate, how fast we heat things is going to be equivalent to a power. It's going to be how much energy per second is being transferred from one of your objects to the other. It's going to measure that thing in watts, energy per second. Okay, so there's an equation. You ready? Here we go. This is now power, P power, not P momentum or P pressure or P, what other powers? Pressure, I think there's even one more P we've seen this semester. It doesn't really matter. This is power equals Q, which is the energy lost or gained by, the thermal energy lost or gained by the system. I'm going to give it a subscript C to denote that it's the energy that you've lost or gained by conduction specifically, divided by delta T over a given amount of time. That's sort of the definition of the conductive power. How much thermal energy you've lost or gained, but divided by how much time has elapsed. So what does that equal to? Let's write some things down and then we'll define them. Capital A over R times TH minus TC. And so here is that delta T. power is proportional to delta T. There it is. What is the proportionality constant? It's A over R. So let's define all of these things. PC is the net energy into the colder object per second. Or per unit time, it doesn't have to be a second. A is the surface area of contact. And R, obviously T hot is the temperature of the hotter object. TC is the temperature of the colder object. Maybe I should actually write those down. I didn't have it in my notes, but let me write those down. TH, TC are the temperatures of hotter, colder object. And what is this R thing? This R is called the thermal resistance. What are the units on thermal resistance? Anytime we come into contact with a new parameter, it's always a good idea to just back up and figure out what units it will have. So we can probably figure it out over here. We've got a meter squared on the right. We've got a temperature on the right. We've got an energy joules per second on the left. Put all those together. We need meters squared per Kelvin to cancel out the units on the right. And we need per watt to cancel out the unit on the left. Or if you want to split watts up into kilograms and meters and seconds, this becomes seconds squared kelvins per kilogram. But I think the first is probably a more intuitive way to think about this. I don't think there's a fancy name for this. For a meter squared Kelvin per watt. Maybe if you devote your life to studying thermal resistances, this unit could be named after you someday, who knows? Okay, so this is, interestingly, why do we call it thermal resistance? It's similar to electrical resistance. How so? Well, you know how electrical resistance works. Electrical resistance is delta Q, meaning delta charge over delta T, right? So in this analogy, our power is equivalent to the current. Our Q in this case is a thermal energy, and in this case it's a charge divided by delta T. And we know that this is delta voltage over delta R, right? From Ohm's law. So delta voltage is equivalent to our delta T, delta temperature up here, divided by R. Sorry, this isn't a delta R, it's just an R. There is no such thing as a delta R, it's just the resistance of the circuit, right? So this thermal resistance is set up to be mathematically similar to electrical resistance, and it works similar to an electrical resistance. R is a measure of, just like electrical resistance is a measure of how hard it is for electrons to pass current through. Thermal resistance is a measure of how hard it is for thermal energy to pass through a particular system. And also like electroresistors, the R's add in series. So in other words, if you had, let's say, 3 substances put together, let's say R1 and R2 and R3, and you want to know what the total electric resistance or thermal resistance of all 3 of them put together is. If this were electrical resistance, you just add, our total is R1 plus R2 plus R3. Same here. If you want the total the thermal resistance, you just have to add R1 and R2 and R3, and you get the total thermal resistance of the system. R tote equals the sum of all of your individual resistors. Okay, has anybody spent time insulating your house or thinking about insulation for your house? Congratulations. I'm glad that none of you have had to think about that yet. There may come a point in your life where you're thinking about thermal resistances and R values for insulating your house or your apartment or condo or doghouse or whatever it is you're sleeping in. You will come across a unit there called R value. R value, you might see, oh, our R value for this insulation is 3. Our R value for this insulation is 5. This is a measure basically of thermal resistance. They're not going to give you units with it. You're going to have to look it up if you really want to know the units, and you'll cringe when you do, because I'm about to tell you what the units are. So for example, fiberglass has an R value of about 3 per inch of thickness. So what does that mean? What 3 what? You might be asking. Turns out that this R value, this is not R, this is the R that we're talking about, but this particular R has a particular unit. And so when you say R value, you're talking about R in this particular unit. What are the units, you might ask? Of this particular R, sorry, I'm not gonna do that because I already did it before. This R, this 3 will have units of feet squared, degrees Fahrenheit, hours per BTU, which may be the worst unit in the history of units for a physicist. Now, if you're wanting to insulate your home, it's actually a pretty convenient one to use, because you might know what the square footage of your attic ceiling is. And you might know what the average temperature difference in degrees Fahrenheit is between your attic and the outside in the wintertime. And you might know how much BTU your furnace puts out, for instance. And this might tell you how good this insulation is actually going to be in units that how much energy you're going to lose per hour out of the surface, given all those numbers. So it's actually a convenient unit to use if you're doing this in real life with real English units, but no physicist would ever want to use that particular number for obvious reasons. That's a good question. I don't know. I've never even really had to think about this with my house here. Certainly never have had to think about this in Europe, but it's a good question. My guess is they use different, but I don't know. These numbers are important, obviously, units matter, but if you know that your R is 3 per inch of thickness or 6 per inch of thickness, you know that the one that has 6 is 2 times better than the one that has 3, right? So at least there you can make a relative judgment on how much you're going to spend based on what the R value of that insulation actually is. So it does scale in that way. Okay. Yikes. Still, the higher the R value, the slower the energy transfer. And the better the insulation. Okay, we will do some problems based on this and think about all of that more on Friday.